So, hello everyone, I'm Pascal and I'm presenting my survey article on efficient frequent subgraph mining in transactional databases. So, what is this all about? It's obviously about graphs, and just to briefly mention, graphs, as you might know, are a very general way of describing things that happen in the real life whenever objects somehow are connected to other objects. So, for example, you can have, as here, a co-authorship network, like from me 2 years ago, roughly, where the objects that might be connected are persons, and they are connected in this case here if they wrote a paper together at some point, right? Another way that's also very important in the context of frequent subgraph mining, because it's an application that more or less started all this, is chemical molecules, where you have little atoms that bond together to form these larger molecules, and you can describe these molecules as graphs. And so basically there are lots of other ways of having data that's, well, basically is easily described in forms of graphs, but not necessarily easy in other notions of traditionally tabular data, for example. So once we have these graphs, it's in our field, of course, directly the next question is how we can learn from this data in this form, right? And as I mentioned, graphs and tabular data are somewhat, well, not easy to be moved one into the other. And so we basically have lots of methods that not directly work on graphs. So basically, you need to transform these or find anything that works with graphs. And one way of doing this would be using similarity-based methods, where you argue that objects that are close by, in this case graphs, that are somehow, well, similar, behave similarly with respect to the thing that you want to predict, for example, right? But then again, the question is, what does close by mean if the objects are graphs? Another way of learning from graphs, so to say, is identification of relevant patterns that you could use for exploratory further analysis or for defining similarities based on common structures that are relevant to you. And here, then the question would be, what is a pattern? What exactly would you consider to be a pattern? And what is the notion of relevancy that you want to consider? Frequent subgraph mining, or frequent subgraphs in this case, are a notion of relevant patterns that you can use for these two tasks before, and are defined as follows. So let's say you have a database of graphs, which are called transaction in this case, hence the name transactional databases. Now you want to find the frequent subgraphs. And this is a reasonable choice, for example, to define similarities. And in detail, this is defined as given a graph database G, D in this case, and an integer threshold, we are tasked to list all the connected graphs that are subgraph isomorphic to at least T graphs in D. Subgraph isomorphism, just that we're on the same page, is a mapping from the vertices of the pattern graph, G1 here in this case, to the vertices of the transaction graph, G2, such that whenever there's an edge in G1 between two vertices, there must be an edge between the images of these vertices in G2. This is the most natural or intuitive notion, at least for me, to define whether a pattern graph is contained in a larger graph. This problem is obviously NP hard. This makes our life a bit difficult here. Nonetheless, there are lots of exact algorithms solving the frequent connected subgraph mining problem. On the lower part here, you see lots of them. And we are also looking at the special case when you're interested in only listing the patterns that are trees. And as you see here, as this is a survey article, you see these methods, but I won't go into the details of what they're actually doing. As you see, there are lots of methods that solve this. And now you're wondering, right? We're in 2020 in a conference. Why are you seeing a survey article here about a problem that was solved 10 years ago, or even 15 years ago, let's say? Well, all these methods enumerate the full set of frequent subgraphs. What's this all about? And the answer lies in the question that I want to ask you rhetorically. So let's say an acquaintance of yours has 200 graphs, and they are not too large, 10 to 30 vertices each, 30 to 120 edges each, and there are some vertex labels, and this guy wants to find the frequent patterns with 5 or more vertices in this database. Can you do it? Well, the answer is no. And the reason for this is actually the computational complexity of this mining problem. And so we will be looking briefly into this, looking into the notions of complexity that might be useful for listing problems, and ask whether there is any hope for the exact mining, and give a revisit to the exact algorithms and their efficiencies, and then look at some more current inexact solutions that might hopefully convince you that there is still progress in this area, and there's also still some questions that need to be addressed, in my opinion. So recall the frequent connected subgraph finding problem is this database, and you want to list all the graphs that are subgraph isomorphic to at least T graphs in this database. Subgraph isomorphism is NP hard, but well, there's more to it, because what you are dealing here with is a listing problem, right? You want to you don't want to answer a yes/no question, but you want to return a list of objects that fulfill your requirements. And so if you want to define efficiency notions for such problems, you have to first think about the output that you're giving, right? And the thing here is, there might be an exponential number of frequent patterns in your database depending on the database and your frequency threshold. So we would need an output dependent bound that somehow incorporates the output size into the efficiency notion. Otherwise, you can just answer, okay, no, there is no way of doing this efficiently because we need exponential time to output an exponential number of patterns. So the most general way of defining this would be output polynomial time, where we say our algorithm is efficient if it finishes in a time that is polynomial in the input size and the output size. So basically what this allows is you basically compute, and at the end you output all the patterns that you found. So meaning basically you might have an exponential time in the beginning where nothing happens, and then in the end you get all the results at once. This is obviously not a very interesting notion from a practical point of view, but nonetheless it's a traditional way of defining at least some notion of efficiency, right? More, in my eyes, practical is the definition of polynomial delay, where you bound the time between finding consecutive patterns by a polynomial in the input size. So basically meaning you start your algorithm after a polynomial time in the input size, you get the first results, and then so on after a polynomial time again, you get the second result, and so on and so on and so on. So this is a useful notion, I would say, for the definition of efficiency here. But there's also something in between the two, incremental polynomial time, which I'm not going too much into detail here. You can look at it in the paper. So Now let's go to the frequent connected subgraph mining and the exact algorithms again that you saw previously, right? I mean, there exists software to solve the frequent connected subgraph mining problem, FSG, GSpan, Gaston, lots of several other papers that provide implementations for this as well. But if you look into the experimental results that they show, you might notice that they typically investigate chemical graph databases. And the thing there is that basically these chemical graphs only have very few additional edges on average, like 3, 4, 5 more edges than vertices on average. And hence I would call them very simple in a way. And once you go beyond these very simple graphs, the runtime and space requirements explode. So here on the right, you see a plot on the x-axis. We increase the density of the graphs. And the database that we're considering here is 50 graphs with roughly 50 vertices each. And then basically we have here 50 edges each on average. And then this goes up here to 100 edges on average and to 250 edges on average. And on the y-axis, you see the time that different algorithms here require to solve this database. And then the thing is basically that for 50 vertices and 100 edges on average, so these algorithms tend to not finish in the day, which is sad, right? Because it's a rather small database and we're not able to solve this. And the reason for this is that the frequent connected subgraph mining problem is actually computationally intractable, has to do with the intractability of the subgraph isomorphism algorithm, obviously. And these existing software somehow implicitly use properties of the graph databases, and in particular, that these graph databases are rather simple. So basically, the point of 2010 and also the point right now in 2020 is that there is no system that can reliably mine all the frequent subgraphs or even all the frequent subtrees in arbitrary graph databases or small to medium-sized graphs. So this is a problem if you have data and you just want to have the frequent graphs, obviously, right? And looking at the theoretical side of this is the picture that I showed you again already. Looking at the efficiency notions of these algorithms, what you can see is that basically none or almost none of the algorithms that were published until 2010 and that were exact are actually efficient in the sense that they have polynomial delay, incremental polynomial time, or even polynomial output time, right? The only two methods that have this are free tree miner from 2003 and an algorithm without a name from 2010. But they come with their own problems. Namely, free tree miner only works for forest transactions, so you can only put graph databases in that consists of trees, basically, or forests. And the other one was not implemented. Actually, it has been tried, but it's not trivial, and it was basically stopped this endeavor. So all the other methods that you see here are so exponential in the output size in the worst case, meaning basically exponential in an exponential set in the size of the input. So it's doubly exponential, which is something that you really don't want, right? In the worst case. Resulting in the problems that you saw before in the runtimes, right? Some ways of dealing with this have been proposed in the last few years. And this is where the second 10 years basically come in right now. One way would be to, well, decrease the complexity of the database by making it simpler or smaller. changing the embedding operator from subgraph isomorphism to something that might be easier to compute, or restricting the pattern language to something that is easier to handle, for example, only to trees, and then allowing a certain error in the set of patterns. Either you find too many or you find too little. And various methods basically do various combinations of the following aspects to achieve better runtime results. And briefly looking at these, we see on the bottom from 2009 to 2020, there has been some work. For the frequent subgraph mining part of things, it doesn't look too good in the computational size, but these methods are basically in practice working a bit better than the original algorithms on more complex data. This one does, for example, a compression of the database by removing certain edges from the original graphs to make the problem more tractable in practice. Nonetheless, the frequent subgraph mining algorithms are not able to basically guarantee polynomial delay or incremental polynomial time. But if you're looking at the frequent subtree mining side of things, it looks much better. There have been recent works that basically, by restricting the patterns that we find to trees, are able in arbitrary graph databases to find at least the trees with a certain error. With this, I'm sorry that I cannot give more details in this short presentation, obviously. Please have a look into the paper if you are interested in more details on why efficiency or inefficiencies are basically the case for these methods. In conclusion, please take home the following points, right? Frequent subtree and subgraph mining is an inherently difficult problem. It's in general not possible to do this in output polynomial time, meaning it's generally not possible to do this efficiently. Exact methods nonetheless exist for a long time, but due to the complexity issues above, they only work on very simple graph databases. So basically, in the worst case, they use output exponential time and space, which is a problem once you leave, for example, the domain of chemical graphs. But relaxations of the problem results in efficient algorithms that can guarantee polynomial delay by trading off, well, the completeness in the sense of that you can actually at the moment only find tree patterns, and by being inexact in a way of one-sided error, so that you either find too little or too many of the patterns in comparison to the exact result. And as an outlook, why I think it's important to still consider this area and to do research in this area is, well, one of the questions would be, can we benefit from both aspects, right? And can we combine the exact algorithms up to the point where they stop being well, practically feasible, and switch then over to the inexact algorithms? That this should be possible, I think. As a more theoretical question, a more general question is, can we basically use the insights that we have for the inexact efficient frequent tree mining to find patterns that are more general and contain some cycles, for example? And with this, I want to stop my presentation, and I would be happy to start a discussion about this. Thank you.